Assalamu alaikum. Welcome to the last lecture of this course. And in this lecture, we will look at why we are finding the stresses at different loading condition. We will overview the usage of that mechanics of solid course. And we will discuss about the yielding criteria as well for this in this lecture. It's a general lecture, not specific to any more technicality or derivation or mathematics, but it gives you an overview why we are finding the stresses under different loading condition and what is the effect of combined loading to any structure or mechanical member. Okay, now failure criteria, any material or structure may fail when it's loaded. Okay, so for example, why we are doing this, for example, we have a structure, a machine member subjected to external load, and that will cause internal forces. And intensity of those internal force we are finding. So internal force can be normal force, it can be tensile or compressive, it can cause bending moment, right? It can cause shear force due to transverse load, or it causes twisting moment, or we call it torque. And we know that how to find the stresses for those conditions. For example, for normal force, we know that the stress is equal, normal stress will be P by A. And for the bending, we know that bending stress is generalized formula I can write maximum on MC over I. And shear force, we know that shear stress VQ over IT that we've used. And the twisting moment, we know that tau is equal to Tc by J, right? So, and that can cause deflection. For example, normal stress that can cause extension or contraction, whereas the bending stresses or bending moment cause deflection or bending, and the shear force and the twisting moment will cause distortion or twisting on the structure. And we know that how to calculate, except for the shear force, because it's a complex deformation. And with that, with those internal force, we can find what is the stresses and using these relationships. And with the material more properties, Young's modulus or modulus of rigidity, we can find the relationship between stress and strain, provided that there's a linear relationship and we are within proportional, we are within elastic limit. Now, failure can be any of these modes or combination of two modes, but we always study what is the dominant mode. So for that, we need to, what are the stresses, what are the strain. So we have to find the stresses and strain if we have any type of failure. The failure can be yielding, means the structure is yielded, yielding is started, permanent deformation is started. It can be a fracture, means there's a crack and then crack propagates and it causes breakage. And the fracture can be elastic fracture or plastic fracture depending on the material, how it behave, means the fracture can be in brittle state, the ductile material can fail in brittle state or in ductile state. Buckling, that is also known as instability. Long cylindrical structure, they tend to buckle. Even automotive frame, the car frame or car body, they also tend to buckle. Under compressive load, they tend to fail, even though the stresses are within elastic limit. Or fatigue, that is also known as progressive fracture. Under repeated load, the material properties tends to load bearing capability reduces, and that cause structure to fail. Even the stresses are within ultimate stresses. Rupture, that is sudden failure or sudden breakage of the member into pieces. So, but for those type of failure, we have to find what are the stresses on that structure or what are the strain on the structure. So what we are interested the strength of the structure of member. The structure must strong enough to carry the applied load, and load can cause these type of failure depending on the which is a prominent failure. Stiffness, we are interested to calculate stiffness. So that is the structure must be stiff enough to that allowable deformation occur. Means you cannot allow very large deformation in some cases, and sometimes you have to restrict this deformation as well. It must be stable, means the structure must not collapse. Buckling, subjected to applied compressive load. That is stability, and that causes buckling failure. Stress analysis provide analytical, numerical, and or experimental method. So it can be analytical method that we discuss in mechanics of solid theory. It can be a numerical method using some computational tool, usually common FEA software, finite element method, that is our finite element analysis, commonly used numerical method, or it can be experimental method that you will do perform in next semester with the mechanics of solid 2 course, how to find the stresses under experiment through experimental method. For determining the strength, stiffness, and stability of load carrying structure. So we want to find what is the strength or stiffness of the structure or stability using the analytical method. We studied this in this course. Okay, now few example, for example, related to this stunt expansion after stunt inflation. Means this is a common nowadays practice to remove the blockage or to open the blocked arteries. They put stunt, okay, and the stunt cause some permanent deformation. So you cannot do experimentation all the time. So in order to design the stunt or expansion, this you can use the a numerical method and reduce the experimentation. Okay, and this is the deformation stresses on the wall. A bicycle, common example. Suppose you are designing a bicycle, so you identify what are the region of interest and how to reduce the stresses or how to change the cross section or change the material for optimal design. This is showing the numerical simulation of a valve, a heart valve, due to blood flow. So this is showing the stresses and deformation. Okay, this is a buckling. This is a crane. The crane boom, they tend to buckle because of compressive load. Even the stresses are within the ultimate strength of the material. So, but the large cylindrical member under compressive load, they tend to buckle. Even the buckling happen in the thin wall member, thin sheets, as well as the car chases and any structural member or machine member that is under compressive load. We have to consider buckling as well. But in this course, we haven't studied the buckling. But for all, and this is showing the electrical component, the connection. Okay, the connection due to current flow, or signal that cause heating, and the heating is cyclic. Now, if you remember, we discussed that the thermal stresses in chapter 2. So that thermal stresses by changing temperature, high and low temperature, it called cyclic loading, and that the failure in the ICs connection, that is due to fatigue, and that fatigue is due to cyclic loading of change in temperature. This is Comet, first jet airliner into a that was into a service by a Comet. This airplane known as Comet. The company was de Havilland, I think. I don't remember the company. They made these jet planes, and these jet planes have some design flaw. Means that window was not designed considering the stress concentration. So due to cyclic loading that cause fracture, and that the fracture progresses, and then there are a number of incidents, and the aircraft manufacturer bankrupted. This is example, one more example of the failure, sudden failure, brittle fracture. The ship structure previously, before World War II, they were made up of rivets, but due to mass production, they changed the rivet into welding, but the welding has a fundamental flaw. So under low temperature, there was a crack, and the crack propagated even the shipwreck within a month of the service into two pieces, and usually it happened at the low temperature seas at low temperature. So these ships are known was USS Liberty class ship, and they tend to fail. So means there are different mode of failure as shown over here, but for those you have to, the loading are same, the internal loads are same. You can have 4 possibility of internal loads, and you have to calculate stresses for that load. Okay. Now, what are the elastic and inelastic response of the solid? For example, this is a typical stress strain curve of a structural steel or steel, in which you have some A, maybe a proportional limit, B, maybe a yield limit, then C, and then failure. Means you test it under the uniaxial tensile test you perform with some standard. So you have different material properties, and material fail at that F, the value of F. Means it tends to have plastic deformation, yielding, then it has cup and cone, then strain hardening, cup and cone necking, and then it fails. So maybe you're designing that you should have some yielding, or maybe you design for the fracture. This is a stress strain curve under uniaxial tensile test of the brittle material. There is no yielding, it doesn't break into two pieces. Now, if you look at the fracture, that is, the fracture is perpendicular to the axis of the member, means it fail under normal stresses. Whereas if you see for the ductile material, the failure is cup and cone, and that is approximately 45-degree, means they tend under shear stresses, where the maximum shear stresses. Under uniaxial case, you remember that it is at 45-degree. So tau max has the plane of 45-degree, if you remember from the chapter 2. Now, if I draw more circle for uniaxial case, for the both ductile or brittle material, what we have? We have only one stress, that is maximum stress. So other two stresses will be 0, and the Mohr circle will be something like this, and we have maximum shear stress, tau will be equal to tau max. In this case will be sigma max by 2. It's very simple, right? So if you have ductile material, when it will fail? When you have max sigma tau y, it fail under shear. So when tau max reaches tau y, very simple. But for the uniaxial case, but if you have a torsion load, then what will happen? Now if you look at the torsion load, if you draw Mohr circle for torsion load, so you have sigma max, you have sigma minimum, both value are same. So sigma max is equal to sigma minimum minus times sigma minimum. Let me put minus sign, and the Mohr circle will be, so let me draw again clearly. So it will be easy to understand. Now, in this case, this is tau max, and tau max is equal to sigma max. Now what? Means if the maximum stress is yield strength, so the yield tau y will exceed, because we know that from uniaxial case load sigma y, so tau y is 2 times tau y, or tau y is equal to sigma y by 2. This is the material property, and in this case that cannot be possible, right? So when the loading condition changes, depending on the state of stress, uniaxial, it's not any problem. But if you have biaxial or triaxial state of stress, when we have 2D stress state or 3D stress state, it will come difficult. For example, this is for the brittle material and it fail under sigma max, but in that case, that is equal to maximum shear stress as well. So how to link these material property of yield strength with the multi-axial loading? So we will discuss briefly in this course, but in detail we will discuss for the next course, mechanics of solid 2. But just to give you an idea why we are calculating the stresses and principal stresses and maximum shear stress, why we are calculating those stresses. Okay. Now before that, a small concept. So suppose you have a uniform rod subjected to slowly increased load. Slowly means we are making it static equilibrium condition. Now what is happening when we applied load? So that length of the beam changes, and the length is the x amount of length increases, right? So if I plot it, load by deformation curve or deflection curve, so it will be straight line until proportional limit, then it will be non-linear line because the strain will become non-linear. Okay, now if I want to find what is the work done, how much work is done, work is basically what? Force, mathematically it force multiplied by distance traveled. So elementary work, I can say the small amount of work, this will be what? This rectangular area, shaded area. So P multiplied by dx, that is my elementary work. Now if I want to see the whole work done to have a deformation, that will be area under this whole curve, total work done, right? This is amount of work done on that structure or machine member with that load amount of P amount of load. Now if we limit ourselves to linear elastic deformation, so it will be a straight line, right, with an elastic deformation. And if I want to find what is the work done till this point, P1, by load P1, it will be what? Area under the curve, and that is triangular area. So that is 1 by 2 times P1 and x1. So this is known as strain energy. Within elastic limit, right, elastic and proportional limit, if we remove the load, the whole strain energy will be recoverable. So there is no loss in energy within linear elastic limit or elastic limit. Okay. Now, if we divide by volume, now considering the same structure member, that area multiplied by length will give me the volume. So U divided by V, what is happening? P by A is what? Stress. Dx by dl is what? Strain. Now it will change, the limit will change from 0 to epsilon 1 instead of 0 to x1. And we denote it small u, this will become strain energy density. Now, if you look at this formula, so now this is independent of dimension, means it will become independent of dimension. So P dx, we don't have to consider what is load and what is deformation, we only consider what is stress and strain, and we can compare with the uniaxial tensile test. Now, so this is known as strain energy density. How much strain energy is per unit volume is used or required to have some certain deformation. Now, if we deform it till plastic limit, or let's suppose over here, so the strain will be, it will come back to this point epsilon P. Now this triangle amount of region, that energy is recoverable, but this energy is non-recoverable, and that will cause deformation, and the total strain energy density from deformation is equal to area under this curve to E1, that is total one. If you applied load, this total, and this much, the triangle will be recoverable, and the other will be this area, the light dark area will be non-recoverable, and it will be causing permanent deformation, and it will dissipate, or it will transform into heat energy, and it will dissipate as a heat energy. So this, under permanent deformation for ductile material, if we go beyond yield point, so this triangular region energy will be recoverable, this light region will not be recoverable, and it will dissipate as in form of heat, because energy cannot be created or destroyed, it can be transformed one form to another form. Okay, now this is known as strain energy density, and there are some material property associated with. So this is again uniaxial tensile stress strain curve. If we the energy under the whole curve, that is known as strain energy modulus of toughness. That is a material property. Means if you have a material, structure member, machine member of certain material, it's, if you put this amount of energy, it will break. So this amount of energy will require to break that material or member. So if you put this amount of energy, let's suppose this is stress strain curve of some ductile material. So if you suddenly apply this amount of energy, it will break. And this is a material property is known as modulus of toughness. Okay. The energy per unit volume required to cause material to rupture is related to its ductility as well as ultimate strength. Higher the ductility, more the ductility, a large area of curve, higher yield strength, large area of ultimate strength. Means if I have a stress strain curve, something like this, so means it required more energy, even though ultimate strength are not that much. Or maybe I have this type of material, so I need this amount of energy to break. Now it's become independent of dimension. This amount of energy are required to break into two pieces. So if we limit ourselves to proportional limit, then it called modulus of resilience. Means this amount of energy will require to have yielding. So in order to yield the material, you need this amount, put this amount of energy. So usually when you're doing the impact analysis or crash analysis, you usually deal with the energy. Or if you want to find the stresses or similar forces due to cutting, let's suppose you have a lathe process and you want to find how much, how it will cut, how material will behave, then you deal with the strain energy density, those values. Okay. Now, if you look at the strain energy density under yield strength, under proportional limit, that will be sigma 1 square by 2e. By replacing E1 square, we know that epsilon is equal to sigma by E, putting the value, so it will be this value. And till yield strength, this is known as modulus of resilience, and means if you apply this much energy to a system or to a structure or machine element, the yielding will start, the permanent deformation will start. But if you put this amount of energy, then it will rupture or it will break into two pieces. Okay, now, so why we are discussing this? Now, for example, if you have uniaxial loading case, for example, and that is a uniaxial tensile testing we are doing. So we have stress strain curve. Let me draw for the ductile material. Okay, so we have epsilon, we have sigma, and over here the yielding is starting. This is sigma u, right? This is typical stress strain curve for the ductile material. Now if I plot the Mohr circle for this one, So that is what? That is sigma 1. That's it. Other value of sigma 2 and sigma 3 or sigma B and C will be 0. And this is the Mohr circle for uniaxial loading case. This is my sigma axis. Means the maximum shear stress tau max is equal to sigma 1 by 2. Or if you want to write till yield strength, tau y will be equal to sigma y by 2. That is my material property. Right? Now, what is happening if you have biaxial state of stress? Right? Means if you have a plane stress condition. Plane stress condition where we have sigma x, sigma y and tau xy are non-zero, where sigma z, tau zx or zy, xz or tau yz, these are zero value. So the Mohr circle can be like this. Two types of Mohr circle where sigma a and sigma b both are tensile, where sigma c is 0. One case can be sigma A is tensile, sigma B is compressive, and sigma C is 0, right? That we discussed in chapter 7 as well. Now, if you look at this first case, the maximum shear stress is the radius of this circle AB, and in that case, tau max is simply what? Sigma x plus sigma y by 2 square plus tau xy square. Now, if you relate the relationship, means sigma A is my maximum stress. So not necessary if sigma A is equal to sigma y, that tau max will be equal to tau y. No, that is not the case. The tau max will not be equal to tau y. So how to relate the material property under biaxial or plane stress case? On the other hand, if you look at this case, now in this case the maximum shear stress is out of plane shear stress. This one. Again, that is not equal to radius. So again, in this case, if sigma A or sigma max is equal to sigma y, so not necessary tau y will be equal to tau max. How to relate? So there we will see. And if in this case, if we have 3D state of stress, so the tau max in this case is sigma A minus sigma C divided by 2. Sorry, sigma A plus sigma C divided by 2. Again, sigma A is sigma y, but tau max cannot be equal to tau y. So when the yielding will start, when the yield will occur. Uniaxial case is very simple. When sigma y is equal to 1 is equal to sigma y, then obviously if we'll take half, so tau y will be tau max. This is the case. Now, there are some mathematical relationship and that is strongly related, supported by the experimental data to find when the yielding will start for the ductile material. Okay, for the brittle material, the same principle, but in that case, it will not yield, it will simply fail into two pieces because there is no yielding. So the yield criteria, in general, we call it a mathematical postulate, is defined by a yield function y. This is my yield strength, and that is under uniaxial load. Means this yield strength is the material property that we find with under uniaxial load, UTS, universal tensile testing through universal tensile stressing, and we relate with the history of stress state. Means if you have 2D stress state, plane stress, or 3D stress state, or maybe if you have 1D stress state. So how to relate? Okay. Now there are different criteria. First one is known as maximum principal stress criteria for the failure of material under loading condition. and it is used for the brittle material because brittle material they are weak under normal stress. So this is known as maximum principal stress criteria. That is commonly mostly used criteria for brittle material, and that was proposed by Rankine. If you remember from thermodynamics, the Rankine cycle, the same scientist that proposed this criteria. The another criteria for brittle material is known as maximum principal strain criteria. So we didn't discuss about this principal strain, but we know the strain, normal strain. So maximum strain on the structure is known as principal strain. It's sometimes used, it's not that much used for the only for the brittle material. And again, this was proposed by Saint Venant. It was proposed by Saint Venant. If you remember Saint Venant principle, the same person that proposed this. Then we have strain energy density criteria. That was proposed by Beltrami, but not widely used because it has some drawback. So most commonly used for the brittle material is my maximum principal stress criteria. We will see. Now for the ductile material, there are two most popular criteria. First one is maximum shear stress criteria, also known as Tresca criteria, proposed by Tresca. And we will see what is the maximum shear stress criteria. Means when the maximum shear stress is equal to tau y of the material, then the yielding will start. Now another one is known as von Mises criteria, or also known as distortion energy density criteria. It is the most popular for the ductile material. So these two criteria are for the ductile material, and these three are for the brittle material. But for the brittle material, most commonly used is the maximum principal stress criteria. But for the ductile material, these two criteria used widely. Both predict almost the same value, almost in some cases. In pure shear cases, it's a 15% difference, but most of the material you can predict the behavior using these criteria. Okay. So yield criteria for ductile materials. So for example, under uniaxial load, we simply know that the yielding will start when sigma is equal to sigma y, right? Failure machine components are subject to uniaxial stress is directly predicted by the equivalent tensile test. But if we have, let's suppose, transverse load, now in this case, we have shear stresses as well. So machine component subjected to plane stress cannot be directly predicted from uniaxial state of stress, tensile test. So we need some criteria. So it's convenient to determine principal stresses. Now, again, why we are calculating principal stresses? Because we have to predict the yield criteria and we need the principal stresses. And based on the failure criteria, depending on the material, what material we have brittle material or ductile material. If we have brittle material or ductile material, so we will use this principal stresses for the corresponding state of stress for the failure criteria. Again, we must know what are the principal stresses. Failure criteria based on mechanism of failure allow comparison of failure condition of uniaxial test and biaxial component. Means these failure criteria is basically linking your sigma y with the biaxial component loading, or you can say the plane stress component. So they are linking these criteria, linking the material property with the biaxial or plane stress state. But later, when you study mechanics of solid 2, so this will extend to the 3D case as well, general state of stress. Okay. Now the first criteria we call, that is for the brittle material, we call it maximum principal stress criteria under plane stress. So what is this criteria? Brittle material fails suddenly through rupture or fracture in tensile test, the failure condition characterized by ultimate stress. Means according to this criteria, when any of the principal stress, now let's suppose you have a general state of stress on a material. Let me write under plane stress. So you have sigma x sigma y, and you have tau xy, where sigma z, tau xz, or let me write tau zx, both are the same component. Tau yz and tau zy, these also are same component, will be equal to 0. Now if you want to find the principal stresses, so sigma a will be sigma average plus radius, and sigma b I can write sigma average minus radius, where sigma average is simply sigma x plus sigma y divided by 2, and the radius we know that sigma x plus sigma y divided by 2 square plus tau xy square under root. Now according to this criteria, and we for the plane stress sigma c is equal to 0, you know that. According to this criteria, if absolute value of any one of the principal stress sigma a or sigma b is absolute value, I'm not talking about the compressive or tensile, it should be absolute value. If it's greater than become sigma u, or it may be equal to the, then what will happen? The structure will fail, and that is for the brittle material. Okay. The structure components save as long as the maximum normal stress is less than ultimate strength of the tensile specimen. Again, maximum normal stress, and this maximum normal stress is your principal stress, maximum principal stress. So if I want to represent graphically for the plane stress case, so we have sigma A, sigma B. Inside this region, my design will be safe. Okay, this is criteria for the brittle material. Okay, now what happens if you have a ductile material? So one criteria of ductile material, that is maximum shear stress criteria, and also known as Tresca criteria. So we call it Tresca criteria also because it was proposed by Tresca, also known as Tresca criteria. So according to this criteria, structure components save as long as the maximum shear stress is less than the maximum shearing stress in the tensile test specimen at yield. Mean that if you know the tensile test is under uniaxial tensile test, so in that case tau y is equal to sigma y by 2. That is my material property. So as long as the tau max is less than tau y, and that is equal to sigma y by 2 as well, sorry, equal to, so in that case we have maximum shear, so the material, the structure is safe, yielding will not start, permanent deformation will not start. But now it can be two possibilities. First possibility, that sigma A and sigma B both have same sign, means sigma A is sigma B both are tensile, or sigma A or sigma B both are compressive, whereas sigma C will be equal to 0. Again, we are talking about plane stress case. So sigma A and sigma B are my principal stresses. So in that case, what will be the Mohr circle? It can be either like this, if both are, where sigma A, sigma B both are tensile, or if we have both are compressive. So in that case, the compressive Mohr circle will be sigma A over here, sigma B, and this is my Mohr circle, and the third circle will be like this, right? So in that case, the maximum tau max is either equal to sigma A by 2 or sigma B by 2, any one of the maximum value, but absolute maximum. Okay. Now, if the case is that both are opposite sign, means sigma A is tensile and sigma B is compressive. So in that case, sigma C is 0. So in that case, the tau max is this value. Again, this is equal to radius of the circle as well. So this tau max is my in plane. in plane maximum shear stress. So if the loading condition is such that this is the case or this is the case, so tau max is my out of plane. Maximum shear stress. Okay. So you have to be careful what are the principal stresses, what are the nature of the principal stresses. Based on that, the maximum shear stress can be in plane or out of plane, and then you will equate with the tau y or sigma y by 2. Now, if I represent graphically, so these are the boundary inside. If your stresses are inside, so your design is safe. If it's outside, then the yielding will start. So that's how you relate your biaxial state of stress or plane stress state with the uniaxial material property. So this is known as maximum shear stress criteria, or in some cases or some literature you will find as a Tresca criteria. Okay. Now last criteria we will discuss, that is known as yield criteria, ductile maximum distortion energy density criteria, or the most commonly known as von Mises criteria. In some software you will find the von Mises stresses. That is basically directly predicting the failure of the criteria. So this value, if I take under root of this value, sigma AB plus sigma B square, so this will become my von Mises stress, and if this von Mises stress sigma E is equal to sigma Y, then failure will occur. So that is the most commonly criteria used in the calculation. Why, we will see. Okay. Now, according to this criteria, the structural components say that the distortion energy per unit volume is less than occurring in a tensile test specimen at yield. Means strain energy density, if you remember, it has two components. One component will cause change in the length, that will cause only normal stresses. The other component, that we call it sigma, let me put sigma V, UV, small uv. The other component will cause distortion. So this strain energy can break into two components, sigma y and uv and ud. So the volumetric part, that will not cause failure in ductile material, only distortion part, because the ductile material, they weak and shear causing the distortion. So the distortion energy, if it's equal to the distortion energy under uniaxial tensile test, means that is sigma y over here. So not the strain energy, only the distortion part under uniaxial tensile. So that is equal to 1 by 6 sigma y square minus sigma equal to 1 by 6 g times sigma y square, and this is the under plane stress case. What is the distortion energy? 1 by 6 g, that is g is the modulus of rigidity here, sigma a square minus sigma a b plus sigma b square, where sigma c is 0, and sigma a and sigma b again are my principal stresses. These are my principal stresses. Now, if this value is equal to sigma y square, or if I take under root on the both side, so this will become sigma y. If this under root value is equal to sigma y, the yielding will start. So that is how the plane stress case is related to the uniaxial material property. Okay, so this is known as maximum distortion energy density criteria, because only distortion part of the energy is causing the failure, not the change volumetric part. And that criteria is known as von Mises proposed this criteria. Now, why it is famous or most popular? Because it can be defined mathematically very. Now, the popularity is due to easy to use, because if you look at this relationship, it's equation of ellipse. Now, if we compare it for the ductile material with the maximum shear stress criteria. Now, if I draw it graphically, represent this criteria, it is an ellipse. Okay. Now, if I compare it with the maximum shear stress criteria, so this is my maximum, inside this hexagon is my maximum shear stress criteria. Now, this hexagon cannot be easily represented mathematically. So that's why and this is easy continuous function, so it is easy to define mathematically. So that's why the von Mises criteria is used widely, especially for the computational tool. Now, if you look at this under uniaxial case, they predict the same value, but under pure shear, they predict slightly different value. So that is roughly around the 15% difference under pure shear. Both the criteria they predict for the maximum shear stress criteria that predict the shearing at 0.5 times sigma y, but for the von Mises criteria it is 0.577. Means if so if it's only the difference of 15%. So, but predict the same value. Otherwise, if other loading case, the difference is very small, but under uniaxial loading, it predict the same value. Now, if my von Mises stress or this sigma e value is inside this region, then my design is safe. Otherwise, the yielding will start. If it's on the boundary or outside the boundary, means under that loading condition, the yielding will start. Now, these are the different criterias. The general yielding, the critical value, just showing from the uniaxial tensile test. What are the critical value from the uniaxial tensile test? For maximum principal stress, is the sigma y. For maximum principal strain, because we didn't discuss, because it's not used widely, that is epsilon y, means the strain at yielding. Strain energy density, that is for stress strain curve under the till yield. Maximum shear stress criteria when tau y is equal to sigma y or py. So py by 2a, that is the load divided by area stress, or sigma y by 2 or y by 2. Distortion energy density criteria, that is equal to y square by 6g modulus of rigidity, and only the distortion part, not the volumetric part. Or this volumetric means that causing only the change in dimension. Distortion is change in angle, that is distortion. The shape is distorted. And the another form of the distortion energy density is octahedral shear stress criteria, but this is not, we are not discussing that. You will discuss later in your mechanics of solid 2 course. So now the material property under uniaxial test, we compare it, or we correlate with the stresses under multi-axial loading, and these are the different criteria. But the most, for the brittle material, the most commonly used is the maximum principal stress criteria for the brittle material, and for the ductile material we have maximum shear stress criteria and distortion energy density criteria. And one variation of distortion energy density criteria is octahedral shear stress criteria. Now, we will discuss more in interactive session regarding this lecture, but this is just to give you an idea why we are calculating stresses, and if we have biaxial state of stress or plane stress case, so how to find the failure or yielding criteria for ductile material as well as the brittle material when you're designing something. And you will use in design of machine element 2 course as well. And in detail, you will discuss in mechanics of solid 2 course. So thank you for your patience and for your support during this pandemic on the online lecturing. And your positive creative feedback is always welcome. So thank you very much. Take care, and thanks again.